A2 等于 A3，然后全部都是 A1啦，A1 A2等于 A1，然后 A3等于 A1，全部都是，这样它们加起来就会有要加也是 A1嘛，全部都是 A1，直到 A，直到第一个 A，然后我们就总共会有 M 个 A1，然后呃，其实好像也不能这样比较，不能这样比较，一这样比较，先让他们全部乘啊，先让他们全部乘到是那个。OK，然后我再把它们全部加起来，这样它就可以打赢。对，我要做，等下我要做一个比较了。啊不，对，然后我这边的话就是如果我要把全部的把它等于一的话，那就是 A AM，然后我再把它 里面下去，里面贴那个什么贴那个什么名字啦，我发现到他们两个是一样的，yes，因为这个我可以用另外一个方法来做。就是我发现到这个里面对发现到他们都是 A1，在想的话，这样我可以被反推去这两个都反面就是这个跟这个是一样，
没有啊，你这个讲算，这个是什么？这个讲算，
这个是这样。哎，擦掉吗？擦掉没？没有，这边嗯，先把一带进去，就先没有，就好像上次一样。
在做么？这个过后变这个，这个过后变这个。
Yeah, yes，真的啊 yes，因为他们那个 loan 可以把它分开。但是不用变得上，第二个到底要，你加一个 M，加一个 E 啊，加一个 E 啊，所以这个应该是M，
那你一个 M 让那个 N 走去 infinity，哦，那个 M 是 fixed 的，对。
加一个 E，这边加一个 E，有写的，
那你得到这个东西是零，所以你得到这个是 log A1，那你就直接 prove 了啊，你拿那个包来做嘛，你不是不用包呢，你不是直接做到 prove 到了吗？
没有，还是一个数字来的，
什么数字 A1 是一个数字
还有
来的
没
，A1是一个数字，
，A 也是一个数字，
对啊，你不是算到了没？你还要包什么？你不是算到了没？你不是
明秀跟我讲什么？那怎么等于几？
因为不，我不知道没就跟你讲，but anyway，就是说你不是直接算了吗？你
啊，
嗯，OK，
这是怎么？因为真的一个数字，就讲1、2、3、4，不是？
A1 啦，A1就是一个数字啊，A 是一个数字来的，这些 A 都是一个数字啊，都是 constant 的。
对，
哎，等一下我再跟你聊，要开始了，然后我再跟你聊。 Someone help close the door. Please. Huh? Who else? Oh, okay. And the last one, close the door. Larry. Okay. All right. Good afternoon to everyone. How's your assignment going? Huh? Still doing it? Huh? Like, almost done. For 500. Do you get stuck or not? Oh, okay. Huh? Level 6. Haven't tried. Already tried? Yeah. I still got office hour Wednesday, so if you want to come Wednesday. Okay. Yeah, Wednesday. Wednesday midnight deal, right? Is it? Wednesday? Yeah. Wednesday morning, I still got office hour. But okay, our midterm will be on around when's our midterm? Do you know? Week 8, huh? Okay, I think most probably it's week 8. We will do it in class. So either we'll pick today or which day? Thursday. Okay. Yeah, one of the day. I will decide when the times come. And then you can bring a cheat sheet. Okay, A4 handwritten cheat sheet. Handwritten, no printing. I don't want you to take advantage of technology, no printing. Okay, you can bring cheat sheet, whatever you want to write on it. Okay, 2 pages A4 size. Okay, don't bring A3 here. A4 size, handwritten. Okay, only handwritten, cannot typeset. Okay, otherwise I'll confiscate your cheat sheet. Okay. Standard time is 1.5 hour. I will see, depend on what question I give. Maybe we can go until 2 hours at most. Okay. Yeah, because it's a test, not a midterm, so we have a bit of freedom doing it. Okay. Adjusting the level of difficulty. So to prepare for your midterm, right? Definitely you should do tutorial question. Okay, you must do it. Okay, and then not just doing it, you must understand what's the question asking. Okay, think about what's the concept the question want to ask about. Okay, you need to get familiar with the concept because in the exam I'll mostly test on concept. Okay, we will have computational question, but concept will be part of it. Okay, concept. Maybe I'll release some practice exam for you to do, maybe 2-3 weeks before. Okay, so that you can get some idea. Yeah. Okay, any question about lectures or not? Past lectures. Have you done all the homework question? Huh? You get laugh on me. Do must try. Don't left until last minute. Too many things to study later. Okay. Yeah. And then you have question, quickly ask me. Okay. Quickly ask me. You can send through Teams. You can see me in office hours. You can email me. Any route you can reach me. Okay. So you got do or not? Tutorial question. Haven't. Okay, very honest. please do okay. Otherwise, you won't get on top of the knowledge. Okay, before we start, let's start with paradox. Okay, I want to talk about one paradox. For last year, I included this paradox in the assignment question, so they know all about it, the previous batch. But I removed this question from your assignment, and instead I put another question, which is the cutting the ruler into half infinitely. So there's a similar paradox here, which is called the Zeno's paradox. Everyone see? Zeno's paradox. Everyone see? Okay. Hard to see. Okay, Zeno paradox. So Zeno is a philosopher, Greek philosopher. So what does Zeno do is he take the strongest man in this world, called the Achilles. You know Achilles? You know Achilles heel? You know Achilles heel? So it's the strongest tendon in your body. Strongest tendon in your body. Okay? Like if you jump too much, then maybe you'll break. Okay? Especially a lot of badminton players break the tendon. Achilles heel. Okay? So it's the strongest tendon in your leg. Okay, so this Achilles, so he led Achilles to run after a turtle. Okay. The ninja turtle. Okay. So first, there's a distance between them. Okay, there's a big distance between them. So Achilles is very strong, so it runs very fast. Okay, so but like all you know, turtle runs slowly. But actually, turtle can run quite quick if you see some videos in the YouTube. But let's assume a turtle runs slow. So he want to ask a question whether the Achilles can reach the turtle or not. Okay. Who say no? Man? No. Oh, you say no. Okay. I will give you the condition yet. Okay. Sorry. Oh, you see this story before. Okay. You think no. Okay. You feel like no. They tell you no. Oh, okay, okay. They tell you no. Okay, let's see how I tell this story then. Okay. Okay, they tell you no. Okay. So this guy runs slow. Okay. So so how to catch up the turtle? Right. So to catch up the turtle, Achilles must run at least the initial distance. Right. Okay. But once he reached this distance, right, he already spent some time. That means turtle already keep moving on. Okay. Then Achilles need to spend more time, okay, to reach the turtle. But the turtle, although it moves slow, okay, but it's still advancing. Okay. So you keep repeating this process here. Okay. So the question is, can you repeat this infinitely many times? Okay. Okay. So let's do it, let's compute it mathematically. Okay. We turn this into a mathematical question. Okay. So how do I turn this into the mathematical version? So I need to measure the velocity. Okay. How fast they run. So let's say, okay, Achilles run 10 meters per second. Okay. And then the turtle run 0.01 meter per second. Okay. And then the initial distance is 1000. So what happened is to cover 1000, how many seconds you need to spend for Achilles? Answering. Yeah, 100. So after you spend this 100, right, the turtle is still keep moving. So we assume the turtle is keep running. So after 100 seconds, how much the turtle run? It's just 1 meter. Sorry, 1 meter? Yeah, 1 meter. Okay. And then to cover this 1 meter, Achilles need to use 0.1 second. Okay, and then after Achilles run for 0.1 second, the turtles run for 0.001 meter. Okay, and then to cover this 0.001 meter, Achilles need to run 0.001 second. Okay, and then we repeat this process here. Okay, did you notice something? Did you notice anything? Sorry. Okay, the Achilles arbitrarily close to the turtle, you mean? Okay, okay, sure. Okay, okay, good. Any other idea? No? Good. Ivan, right? Okay, good. Okay, respect your thought. How about the rest? Any other idea? Unreal? Huh? No idea. Okay, how about the rest? Any other idea? No idea. Okay, what can you see about this times here? Does this time form a sequence or not? What sequence is this? Geometry sequence with radius what? With ratio what? 1/1000, which is 0.001 second. Okay, so this is a geometric sequence. Okay, so geometric sequence, if I add them up, become a geometric series. Okay, so if I consider the total time it takes, what is the total time? Which is the sum to infinity, sum of time to infinity. What is sum to infinity? What's the formula? A over 1 minus r, which is 100 in this case. The first term, 1 minus 0.001 second. What's this? Huh? 1? 1? I think need to do some calculation. 0.999. What's 1,100 divided by 0.99? 100.1001. Okay, second. So this is the sum of infinity. Okay, what does this mean? So if you multiply this time to the velocity that Achilles take, what do you get? This equals to velocity times time, right? So velocity is 10 meter per second, and then multiply by 100.1001 second, which is equal to 1,001.001 meter. Okay, so this means what? So this means Achilles will reach the first of the tortoise at 1,001 meter. Okay, this match our equation, right? So the other run faster, the other one run slower. Okay, so yeah, okay, okay, okay. So Zeno says that you cannot do it because you can do this process infinitely many times, but the series converge. Okay, but the series converge. You get a real total number, a real total time. Okay, yeah. Although you think that you can do it infinitely many times, but actually they sum up to a finite number. Okay, it doesn't add to diverge. Okay, you cannot reach that person means you take infinitely many times. Okay, but here we take finite times. You guys are still fresh, is it? Are you guys still fresh? Still fresh, huh? Okay, later maybe 1 hour or 2 hours after I show you one video. Okay, I show you one video about series. Okay, later I'll show you. Okay, let's resume what we did last time. Oh, where does we left? Okay, so let's resume what we did. Okay, so we stopped at a theorem, if you remember. So we stopped at the term by term differentiation and integration. Okay, so what does this mean? So first you have a power series. Still remember what's the power series is? What's the form of power series? 1 over. Oh, you remember the other function, is it? So power series is what? Power of what? Power of x. Okay, sum of power of x. So in particular, you have some coefficient. Okay, multiply by x to some power. Okay, but remember, we can shift the power series. Okay, just like how we shift y equals to x to y equals to plus x plus a. So we can shift our power series centered at a. And then remember, we want to test the convergence of series, right? In particular, we can test the convergence of power series. How do we test convergence of power series? Ratio test. Okay, very good. So once you test that, you can find out your radius of convergence, okay, or the interval of convergence. Okay. So say we have a function, okay, equal to this power series. Okay, then this power series is differentiable. Okay, not everywhere. Remember, not everywhere, but just on the interval of convergence. Okay, because they might not equal at outside the interval of convergence. Okay, so in particular, if you want to differentiate your f into f prime, okay, you just differentiate term by terms. Okay, so you differentiate your powers and then keep your coefficient. Similarly what? Similarly, you can integrate your function. Integrate your function from 0 to x. Okay, from 0 to x. So you just integrate term by term as well. Is everyone okay with this notation here? This compact short form notation. Is it everyone okay? Okay. So we do differentiate each term and then we integrate every term. So differentiate, you decrease your power and then you multiply by your power. Integrate, you add your power and then divide by your power. Okay. Okay. So in this case here, both radius of convergence are just r. Okay. So the radius of convergence stay the same. Okay, stay the same. Both radius of convergence stay the same, which is r. Okay. So you don't change the convergence condition. Okay, so how we use this? Okay, how we use this? So last time I showed you one example by differentiating. Right? So let's do new example on integration. So for example, yeah, let's determine the interval of convergence for the following function: x plus x squared over 2 plus x cubed over 3 plus x4 over 4. Okay, Yeah, and find the closed form. Okay, closed form or an implicit formula for it. It converges. Okay, so what's the easiest power series you have to keep in mind? Remember, what's the easiest one you need to keep in mind? The first one I introduced. What is 1 plus x plus x squared plus x cubed plus so on equals to 1 over 1 minus x. Is this enough or not? Is this enough? Why not? Absolute value of x must be less than 1. Okay, so that it converge. Outside 1, not the same. Okay. Okay, good. So we have this in mind. And then we want to check for this x plus x squared over 2 and so on. So how do we relate these two things together? How can we relate these two together? Do you see any way to relate them? Huh? Who? Sorry? Factorize? Factorize? Factorize who? X? Okay. Maybe we try. So if we factorize x, what are we doing here? 2 plus x. And then what else can we do? So you can see that this denominator here is like following the power of x. Okay. Yeah. Yeah. Okay. So when does this happen? When does this happen? So how? What are you going to do with this? I'm not sure. Maybe you can try. But what we can do is actually this is the integration of the power series 1 plus t squared plus t cubed and so on. Is it? Right? Right? Yes or no? Right? Because this become a t, this become t squared over 2, t cubed over 2, t to the power 4 over 4. Okay? But if I integrate from 0 to x, the second term cancel. Okay, and then all the t will be replaced by x. Okay. Please compute this if you don't understand. Okay, please compute this integration. Okay. Okay, so if we have this, but this is only true when the t is less than 1. Okay, only you can do this. Okay. And so to integrate 1 over 1 minus t, we just get minus ln absolute value of 1 minus t from x0 to x, which is what? Which is minus ln of 1 minus x. Okay, and this is only true when x is less than 1. Okay, and then from here, s is less than 1, right? Okay, and the center of 1 minus x is at where? 1 minus t. Where's the center? Where's the center? Center of 1 minus 1 over 1 minus t. What's the center of this power series? Zero. Okay, zero, right? Because there's t minus a where a is zero. Okay, so this is center at a. So in particular, we have radius of convergence is 1. Okay, because x is less than equal to 1. And then, so it converges for -1 and 1. Okay, but we want to find the interval of convergence, right? Okay, so interval of convergence, is it from -1 to 1 or not? Strictly. Not sure. Okay, we need to check the endpoint. Okay, because endpoint is where the ratio test is inconclusive. Okay, so we need to check the endpoint. So there are two endpoints to check here. So one endpoint is x equals to -1. Okay, so if x equals to -1, what do we get? We get, what do we get? We get what? What's the series here? This is the series we are interested in. Okay, so we need to plug our -1 in here. So we get x plus x squared over 2 plus x cubed over 3 plus x to the power 4 over 4. In other words, you get what? You get -1 plus half minus third plus fourth, and then alternating of what? Harmonic series. Okay, so this is the alternating harmonic series. So in particular, this converges, okay, which converges as it is an alternating harmonic series. Okay. Okay. So far, okay. Okay. So how about 1? Okay, I think you should guess already or compute advanced. What is 1? So 1 to the any power is still 1, right? Okay, so I just get 1 plus half plus 1/3 plus 1/4. What's this? Harmonic series. Okay, which converges, diverges. Okay. So how do we call this alternating harmonic series? If I take absolute value, it diverges, but it converges if it is alternate. How is the convergence of alternating harmonic series? Absolutely convergent or conditionally convergent? Absolutely or conditionally? Absolute. Condition. Right, condition. Okay? You only converge when you have alternating sign. But if I take absolute of every term, it diverges when you add up. Okay, so it conditionally converge. So it absolutely converge means you take absolute value also converge. Okay, so there's a what absolute convergence test, right? If the absolute value of an converges after you taking some, then the original sequence series also converge. Okay, absolute value convergence sequence. Okay, so this alternating harmonic series is conditionally this. Okay, so our interval of convergence is covering -1, something less than 1. Okay, so you cover the left endpoint but not the right endpoint. Right? So I'll let you try a question. I'll give you maybe 3 minutes to try this question here. So find the series representation or ln 1 plus x. Okay, and then try and find the radius of convergence. Okay, try this. Ln 1 plus x. Find a power series representation. So just now we go from power series to a closed form of function. Now I give you a closed form, and then you give me a power series. And discuss with your friend if you like. Share with your friend. Share with your friend. Okay. Anyone have any idea? Any idea? Have you done? Have you tried? Yeah. Have you tried? How to find? And then
derivative of fx and find derivative of derivative of fx.
are you doing that?
It's just almost
I don't get into Taylor series yet. Uh, sure, but we haven't introduced that yet. Yeah. we will see it soon. Yeah. Two slide. Yeah, two slide ahead. Yeah. So what can we do? Given what you have now, term by term integration, term by term differentiation, what can you do? And then given that you know what is 1 over 1 minus x. How to get long? Integrate what? Yeah. Okay. So in particular, this is the integral of 1 over 1 plus t. Okay. If I set my integration domain from 0 to x. Right. Okay. So remember this trick, 0 to x trick. Okay. Why? Because ln 1 plus 0 is ln 1. Ln 1 is just 0. Okay, so that term disappears. Okay, so you're left with 1 plus ln 1 plus x term. Okay, so why is this useful here? Because we know the power series representation for 1 over 1 minus x. Okay, but this one is 1 plus t. Okay, so how is this related to 1 over 1 minus x? You just minus t. Okay, so this is what we discussed last week. So I can make it 1 over 1 minus t. And in this case here, we can turn this into a power series representation. Okay, but with an extra condition that the t has to be in between -1 and 1. Okay, yeah. Okay, so from here, I can integrate term by term. Okay, because I want to get the power series out of this integration. So how to integrate a sum? Can we integrate a sum? Can? Can? Cannot. So far change your answer. Can or cannot? Why? Yeah. Okay, but you need to be careful here because here is an infinite sum. Okay, you definitely can do it for finite sum. Okay, but here is infinite sum. How you distribute infinitely many times? You need to justify that. This is the key problem in analysis. Analysis is the problem dealing with infinity. Infinitely big or infinitely small. Okay, very small or very big. Okay, this is what calculus is doing or analysis when you go to second year. Okay, we care about this infinite a lot because we can't really define it. So we use finite things to approximate it. But in this case here, we can do it. Why? Because we already have the theorem. Theorems tells us we can integrate term by terms. Okay, this is what theorems tell us. So theorems is very important. So that's a proof of it, but we didn't present it. But if you are interested, please have a look. Okay, and so what does this mean? This means we can commute the sum with integral here. Okay, because we can do it term by term. So do you know what this means or not? What do I mean by commute here? Okay, so for example, I'm integrating a sum, okay, or I am summing the integration, okay. So this is what the second expression represents, okay, sum of integral, okay, and then the previous one is integral of sum, okay. So don't simply swap these operator. Okay, you must know what you are doing. Okay. So this is an example here. Okay, and we can integrate term by terms here. dt. So integrate this term. What are we getting? We are just getting -1 to the power n, t to the n plus 1 over n plus 1 from 0 to x. Okay. Not that we extract this -1 out because notice that this is just -1 to the n times t to the n. Okay, but you are just integrating t. So -1 to the n is just a constant. So I pull it out. And can I make this easier? Okay, so we evaluate the integral, which becomes -1 to the power n times x to the power n plus 1 over n plus 1. Okay. So what's our radius of convergence? The radius of convergence. Yeah. Radius of convergence. We call Roshan. Where's Roshan? Okay. Where's our radius of convergence? Where's our R in this case? Any idea? So what's radius of convergence? Do you know? Converge. Of who? Sorry. Of radius convergence? Wait, what? I mean, what's the radius of convergence for? What's the radius of convergence for? So can you speak louder? Becomes smaller. No. I mean, what is it for? For what? What's the use of radius of convergence? What does it tell us? Radius of convergence is a number. It doesn't become smaller. It is a number. Fixed number. Okay, what does this number tell us? This number tells us something about the series. Okay, when can we express a function in terms of an infinite series? Okay, so which process here we express a function in terms of power series? Which process? Which equation? Number. So I have number one. Sorry, I have number 1, 2, 3, 4, 5, 6. When do we switch from a closed form function into a power series? Huh? Third one, 1, 1, 2, 3. Okay, good. So this is the third one. When can we write this form? What's the condition in pause here? Yeah. So all our points have to be less than 1. Okay. So all our points have to be less than 1. Modulus is less than 1. So this means what? Our t is in between -1 and 1. Okay. And then this is centered at 0. Why is it centered at 0? Because this indeterminate here is just t minus a, where a is 0. Okay, centered at 0. In particular, the radius is the endpoint to the center. Okay, so endpoint to the center is what? It's just 1. Okay, so the radius of convergence is 1. Okay, you get it now? Okay, so very important, you need to know this concept. Okay, so the radius of convergence is 1. How about the interval of convergence? Can you deduce anything about interval of convergence or not? Can you deduce anything? Huh? Let me ask another one. Xiao Tong. What's the interval of convergence? Can you determine the interval of convergence or not? -1 and then 1. Do you want to include them or exclude them? Or how you decide? Which one you choose? Sorry? The last one you choose. Okay, so why you choose the last one? Why you choose the last one? How you choose the last one? How you choose the last one? Any idea? No. Your friend can help or not? Seng can help? Cannot. Okay. Ask Larry. Larry, how to determine this? Okay. 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 Good. So why are we doing that? So I want to ask the question. Always ask the question. Why are you doing this? Okay. I don't care what you do. Why you do is very important. Okay. Why you do? Yes. Okay. So when x equals to the endpoint, it may converge or diverge. So you need to check. Okay. So you need to check because ratio test doesn't tell you anything. Okay. Ratio test doesn't tell you anything. When at this endpoint, ratio test will give you the limit L equals to 0, equals to 1. Okay. So you need to check the endpoint. I will leave it for you to check. Okay. So left as the exercise. Not that when I say left an exercise, actually I already do this example before. Can you quickly see what is this? If you substitute x equals to 1. One over 1? 1 over 2? Why suddenly got 2? Sum of 1 over n or alternating 1 over n plus 1. What's that? Harmonic series again. Alternating harmonic series again. Okay, try and do it. Okay, do it. Okay, we already do it a lot of time. Okay, try and do it. Okay, there's another question in your lecture note. Okay, I will post it the solution later so you can try and solve for tangent inverse x. Okay, I'll give you a hint. So how do you get this tangent inverse x? So you realize it as a integral of 1 plus t squared. Okay, and then try and do the same process yourself. Okay. Yeah. Okay. Because we want to get into one interesting example here, a very important example, and we're gonna use some knowledge from ODE. Okay. Let's try this example. So we want to find a formula, and we want to find a formula for the following sum, which is 1 plus x squared over 2 factorial plus s cubed over 3 factorial and so on. What is this? Okay, we can write this in a formula. Okay, formula n equals to 0 to infinity of x to the power n over n factorial. Okay, n over n factorial. I think we determined this function before. Remember last week we have a power of x multiplied by n factorial or divided by n factorial, and then I discussed about where they converge. When it is dividing by n factorial, whatever number you put in x, this n factorial grow really fast. Okay, it will go really small. Okay, in particular, it converges everywhere. Okay, every point you put into x, this series will converge. But if you swap the n factorial up, okay,
if you consider n factorial multiplied by xn, you can see that whatever number you put in x, n factorial grow really, really fast. So it converges at only 0. Remember last time we did this using ratio test. If you don't remember, you should do it again. Okay, there's no harm to repeat. Repeat is quite important, you know. Did you go to gym? Anyone of you go to gym? No. So you guys don't do sport, is it? Yeah. Please exercise. Please exercise, huh? Be healthy. Oh, basketball. Okay, good. So basketball, what you do? Huh? What? You swing on basketball court? Yes. Okay. Okay. I mean, yeah. So I mean, so when you go gym or when you do sport, right? Typically you are just repeating the same movement every time. Okay. But these movement will help you be better because you get used to it. You get used to it. Okay. Right. So yeah. So it's no harm to repeat question. Okay, if you forgot. So what should I say? So note that this series here converges everywhere. Okay, everywhere. So the radius of convergence is up. Okay. Using the ratio test last time. So this is done last time. Okay, so how to find the formula? Yeah? How to find the formula? There's some special things about this series here. Okay, there's some special things about this series. What can you do? Let's say we can differentiate it. Okay, can we differentiate it? We can. Why we can? Because this guy converges everywhere. Okay, converges everywhere. So let's say it has a closed form, and then we want to find it. Okay, it has a closed form. We want to find it. So if I differentiate this, what do I get? I get 0 plus 1 plus x squared over 2 factorial plus s cubed over 3 factorial. Okay. Did you see this? So the first term, 1 differentiate to 0, x differentiate to 1, and then the power go to the front, cancel with the 2 factorial. So the third term become x. I guess similarly, when the power got bring down, it got cancelled with n from the n factorial. Okay. Okay. But what's the significance here? Okay. What you get is you retain x. Okay. So you differentiate your series, and then you get back your series. Okay. So this is a equation you get from this x. Okay or not? Is everyone okay? So far so good. Okay. Okay. So this is a relation we have on x. Okay, the function x. Xn over n factorial. Okay, so we say we want to do this using ODE stuff, right? So in ODE, we need to have a boundary condition. Okay, boundary condition to have a unique solution. So boundary condition here will be x equals to 0. Okay. So when x equals 0, you can see that all the other terms involve x. Okay, so these x term will disappear. Okay, what we left with is just the constant term. Okay, so it read out the constant term. Okay, now if I substitute x equals 0, okay, what do I get? All the x term disappear. I left with a constant term. Yeah, so we get x 0 is just 1. Okay, have you guys learned separable of variable? Already learned now? Okay, good. So we differentiate xx equals to xx. Okay, so how do we solve this ODE? So we can use the method of separable variable, okay, where we bring dx to the other side and then we integrate. Okay, So this is called method. Why is this called method? Because d over dx is really not a function. It is an operator. It's not a function. Okay, but why we can do this? You need another proof. Okay, you should ask the ODE lecturer to prove for you. Okay, why does the method of separable variable works? Okay, so what's the key point here is d over dx is not fraction. Okay, it's an operator. Okay, and what's the result of this? So, what is this? So we can further move our function xx to one side, and then all the xx to the other side, all the x to one side. Okay, so we are integrating this function 1 over xx dxx. Okay, so meaning we view this xx as a variable. If you want to see it as a y, also can. Okay. Okay. Yeah. So what's this? This is just ln of absolute value of xx equals to x plus a constant c. Okay. So this is an extra constant coming from the integration. Okay. So we need boundary condition to determine the c. Okay. So we further simplify our function here, which we get e to the x plus c, and then what? Then we can bring our constant down. Okay. Actually, we can remove. Can we remove? We can remove this a. Can remove this absolute value. Maybe we don't remove it first. So let's determine what is a. Okay. So when x equal to 0, we get what? X0 is 1. But in our case here, x0 is x0 is what? So yeah, x0 is 1. Okay. And then xx is a to the times e to the x. We can remove this absolute value, right? Because this function is equal to e to the x plus c. E to the x plus c. Okay. E to the x plus c is always positive. Okay. Yeah. Okay. So in this case here, what do we have? X. So we need this. So x0 is also equals to a at the same time. So this implies that a equals to 1. Okay. Then what do we have here? Okay. So all together we have xx equals to e to x. So in particular, this is the power series representation for e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 to the 4 factorial, and so on. And then this is true for all x. Okay. So what does this mean? Okay. So remember how I motivate you on this power series. Okay. So how do you add? Okay. So you have e to the x. You have e to the x function here, which is intersecting at 1. Okay, y-intercept is 1. So you have 1. Okay. And then 1 plus x will somehow shift your function like this. Okay. 1 plus x squared will move like this. And then 1 plus x plus the x cubed term maybe becomes something like this. Okay. And then when you add up more and more terms, you'll see that you will get these functions approximating the ex better and better. And then it converges everywhere. So meaning if you take infinitely many of them, then their difference will get smaller and smaller and smaller. So since they converge everywhere, right, you can really see EX as a sum of these guys. Okay. But note that what? E is an irrational number. Okay, but the left-hand side is the right-hand. Okay, my left-hand side is a sum of maybe sometimes irrational, sometimes rational. Okay, but the left-hand side is always irrational. Irrational except one, except at x equals to 0. Okay. Okay. So you see, sum of some rational number might get to irrational number. Except 0. Don't talk about 0. 0 is the exception. Okay. How about the other? E to the any power is still irrational, right? But here is a sum of rational. You need to take infinitely many. Yeah, think about it. Okay, let's take a break until 4:12. Okay, and then we'll continue. 对，就干过，因为我们是碰这个，这个也是这个情况，要不然就对，好，会，也需要原来都把这个学分把这种状况。
也是这个10号的话，你就变成这样。每次刚有一个出现，操，那个我给发什么？这倒是。不一样。其实看，换的是换的。我记得第一他第一个是第一个题是跟第一题。我记得对吧？对啊，我直接记得。你这个题，你这个第二个选，这个其实是可以写这个，没定想。是用现在这个话，这个那这个
这个要是
前面这个是医生或者裴老师之前不是说对，我应该开始搞我们两个没。那是个晚上，我不知道，可能要。对，是吧？不容易。他老师没有。他就是写作。有这句话是在跟谁说？这是哪一个？因为我那个中间没有加一些证明，验证明是说高人是动物进，我不来，没有证明这些东西。连后头面信息都。这么做把事情做小，就你错了，我错。后来之后，这班都类似于，吓死我了！
Before I start, right, I want to show you a video. I'll show you a video. Let me show a video of one clip of anime that I like that uses knowledge of calculus too. Okay. Do you want to watch in Chinese sub or English sub? Huh? Chinese sub, Chinese subtitle? Okay. So we will spend about 5 minutes and then we will resume. Yeah, I try first. Yeah. Okay, how about I just play from my computer. I think it's currently quite famous now. Like, yeah, Jujutsu Kaisen. Yeah, it's quite trending now. Okay, trending. Let's see we got sound or not.
じゃあ、私たちも向かいましょう。
Yeah.
少し面倒なことになる。いや、式の人は少し違う。悟り天内の首に3000万の懸賞金ああ、重曹師御用達の闇サイトで期限付き。あさっての午前11時までだそうだ。なるほどね。
1、3、4人。みんな同じ背格好じゃん。飛びか
呪術師は年中人手不足だっていうのに。転職するなら歓迎するよ。おっさん。そういうの言ってたらねえよ。友達にどこがいいんだよ。こんなガキ。
髪の毛どれが本体じゃん
式願書ね。同心が。全部本体よな。なんでだよ。僕は大事。自由に選択できるんだろ本体の愛楽なんてな。 じゃあ、なんでこんなに前がいいやね。されたらしばらく後ろが出せないのか。いや、いいもんね。俺の常識はさ、収穫する無限中腹みたいなもんで、俺に近づくものはどんどん遅くなって、結局俺までたどり着くことはなくなる。それを強化する道具加減、あいつと自然数ってとか、虚構が生まれるんだ。そうするとさっき、無理なんだね。あまり大きな反応は、この近くに作れないし、構成にまで気を使い出すと、重力操作が、まあ面倒で、要は、全部順天の術式の話。こっちは無限とされた。術式なんで。だから来そうと思ったんだろうな。
どうしよう。
Can you understand what's going on there? Huh? No. Understand the Chinese word or not? Using no. Using the convergence or divergence or series. And then he talked about the turtles, right? Arcadus and the turtles. Okay. And then there's one phrase very important there. Do you remember what he said? Study is very important. Okay, study is very important. Okay. Yeah. Okay. And then there's the one part he said that he haven't learned enough how to control the direction. I'm not sure you notice that. Okay. Direction is the second part we will learn in calculus 2. It's called the gradient. Okay. We will do that in the second part of this course. Gradient. So after he learned gradient, maybe he can do better. Okay. Yeah, this one is when he is here. Okay. So let's continue. Okay, let's continue. We will do what Han we said just now. Taylor series and Maclaurin series. Okay, Taylor series and Maclaurin series. All right, so Taylor and Maclaurin series. Okay, so let's say we have a power series representation of X, F. Okay. So can we have a form, okay, of describing the coefficient of our file series? Okay, let's say we know what is F, okay, and then we know how to express F in terms of power series. Do we have a formula for our coefficient or not? Okay, so this is the question. What do you think? Can we find Cn in terms of f? Can we find Cn in terms of f? Can we find f? Can we find C0 from fx or not? Just now we already did this. Sub what? X equals to A, right? Sub x equals to A. What happened? All the power terms will disappear. Yeah, and then you're left with F0. So let's write down what we have. So C0 is just F applied to A. Okay. How about C1? How about C1? How to get C1? Okay. Somehow we see this also. Somehow we already see this in the previous example. How we shift the x just now, e to the power x. We differentiate, right? Okay. So if we differentiate once, what do we get? If we differentiate f once, what do we get? What do we get? We just get C1 plus 2 times C2 x to the A, and we have higher degree terms with x. Okay, so let me change the color. Okay. And then plus higher degree term with x. Right. Okay, what can we do? We can do similar thing. We could just sub x equals to A into f. Okay. And then what we get is C1. Do you know how to get C2 now? How? How to get C2? Add more derivative. Okay. So maybe we differentiate again. Okay. What do we get? We're left with 2C2 plus we get 6 3 times so 2 2 times 3 times C3 x minus a. Okay, how about I write another term here and so on. Okay, so how to get C2? To get C2, f prime prime apply to a. That all. Divide by 2. Okay, divide by 2. Okay, how about C3? F prime prime a divide by 3 factorial. Okay, so you can see that there's a 1 over n factorial factor coming in again. Okay, so what is Cn actually? So Cn actually is f to the power n, not to the power. Take derivative n times, okay, apply at a, divide by n factorial. Okay. Yeah. So in particular, okay, just now I give you an example, right? I give you an example just now. E to the power x is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. Okay. So you can see that this factorial is not accident. Okay, it's not an accident. Okay. And then all the coefficient is just e to the x apply at 0. Okay, which is just 1. So all the coefficient here is just 1 over n factorial. Okay. Can you see it? So it's like 1 plus 1 times x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed and so on. Okay. Okay. Okay, can you see the Cn? Cn. Hello. Sleep already. Confused? Any question? No. How about the confused one? Vincent, what is Cn? Okay, so if you write your function in terms of power series, okay, you can get the coefficient of your power series through f. Okay, through f. Okay, through f. Did I say anything weird? Through f. Yeah. Okay, how to find through f? Cn means for all n, okay, 0, 1, 2, 3. Okay, you look for the n derivative of x. Apply at a, x equals to a, divided by n factorial. Okay, remember this, how we find this Cn. Okay, and then verify for yourself for the example e to the x. Okay. I didn't say any complicated actually. So, any question, like any confusion? Because I didn't say any. I'm not trying to trick you here. So. Okay, so this theorem provide a way, okay, a way for us to write out the power series representation of my function. Okay, this provide a way to write down the power series representation. So you don't need to play the trick just now, like always expressed in terms of 1 over 1 minus x anymore. Okay, what you can do is you differentiate your function. Differentiate your function, okay, divide, differentiate your function, evaluate at x equal to a, and then divided by n factorial. That is your coefficient in front of your power of x. Okay, that's the coefficient in front of your power of x. Okay, we will see some more example. Okay, later I show you example. So in this case, what do I mean here? So in this case, okay, what do we have actually? So we have fx equals to f8, okay, plus f prime a divided by 1 factorial times x minus a plus f prime prime a over 2 factorial times x minus a squared, and then so on. Okay, so this is what just now how we mentioned about you differentiate your function, keep differentiating your function. Okay, get your coefficient. Okay, but you need to always remember there's a n factorial dividing here because a lot of people forgot. Okay, they just remember to differentiate and evaluate it, but they forgot to put in this n factorial factor here. Okay, to remember it, you just remember that ex have this n factorial behavior. Okay, later I will show you. So in this case, f equals to this, and then this. So the above series is called the Taylor series. Okay, the Taylor series. Taylor series of f centered at x equals to a. Okay? Centered at a. So this is called the Taylor series. Okay, this is the motivation that I gave you. In the first class. Okay, I draw the picture for you. Okay, approximating a function using a sum. Okay, so what we are using, we are actually using the derivative of your function. Okay, derivative of your function. Okay, so for example, okay, wait. So let's another terminology. So if it is centered at 0, okay, a equals 0, then the series is called the Maclaurin series. Okay, series is called the Maclaurin series. So Taylor series is a generalization of Maclaurin series. Okay. But seems like historically, Maclaurin series come after Taylor series. Yeah, I think when the Maclaurin series come out, only the Taylor series get notice. Okay, so for example, let's find again. Okay, let's find again the Maclaurin series for e to the x. Okay, let's find the Maclaurin series for e to the x. So just now we use what method to find? Just now we use the method of ODE to find e to the x. Now let's use the method of Taylor series. Okay, so let's just use the method of Taylor series. So to do Taylor series, what do you need to do? Okay, so e to the x is equals to f, so is equal to the sum from 0 to infinity, and e to the x differentiating n times, okay, evaluated at x equal to the center point, which is 0 at this case, and then divided by n factorial, okay, multiplied by x minus 0, so x to the n. So this is the thing we need to find here. So what is unknown here? What is really unknown is just this derivative here. Okay, so let's list this down. Okay, list this down. So e to the 0 at x equals 0 is just ex and x equals 0, which is just e to 0, which is just 1. Okay, and then differentiate once. What do we get? We again get ex. Okay, ex is the thing that no matter how many times you differentiate, you still get back ex. Okay. You get what? You get 1. And then so on. Okay, actually, you can see that ex to the power n evaluated at x equals 0 is just 1. Okay. So you sub it in. So we sub it in. So e to the x is actually equal to sum of n equals 0 to infinity of 1 over n factorial over xn. Okay, which is what? Which is just 1 plus x 2 over 2 factorial plus x cubed over 3 factorial and so on. Okay. Is that okay? Yeah. So we have two ways of getting it. Just now we use ODE. Now we use Taylor series. So if I want to determine the ratio of convergence, how to determine? How to determine the radius of convergence? Closed form equals to sine infinite series. How to determine the radius of convergence? It's a ratio test. Yeah. Okay. So you can use ratio test to do it. You will definitely get the ratio equals to infinity. Okay. So use ratio test to compute to get ratio equals to infinity. Okay. So I mean, this is a very natural thing to do. Okay, when you have a closed form equals to some power series, you have to ask, is it true for all x or not? Okay, so you need to use ratio test to test it. Okay, this is a very natural thing to do. Okay, whenever you see this. Okay. Yeah, so this is a Maclaurin series. And then we want to introduce some terminology because later we're going to truncate it. So we will denote the nth degree Taylor polynomial of f at 8. Okay, it's just the n partial sum. Okay, it's just the n partial sum of the Taylor series. we look at the n partial sum. Okay. In other words, the sum, the fx. Okay. So just put a remark here. In other words, the function is what? It's just the sum of its Taylor series. Okay. If fx equals to the limit of your n degree of polynomial. Okay. So you keep adding terms into your Taylor series. Okay. So why do we do this? Because sometimes we want to check the remainder. So we introduce the remainder. So the remainder of Taylor series which we call the Rn, subscript n. Okay. The n remainder is just fx. Sorry, not these r, normal r. R equals to fx minus tnx. So for example, just now we have ex equals to 1 plus x squared over 2 plus x cubed over 3 factorial and so on. Okay. So what is the t2 term? Okay, for example, what is t2x? T2 T2x of ex. Summing from where, which term to which term, if I have a T2 here. Yeah, summing from where? So Tn is summing from 0 to n. So why put that in? So summing from 0 to n. Okay. In particular, here we're summing from the 0 term to the second term, number 2 term. Okay. So in this case here we have 1 plus x squared over 2. Okay. So in principle, we will compare these two terms here. Okay. So the difference between ex and t2x is what? Is the things that left over. Right? Okay. So this is what we call the remainder. Okay. So we take ex minus t2x is the remainder. Make sense? Does it make sense? And see or not? Does it make sense? So we have the ex. Okay. If we take away the t2 terms, okay, what we left is the remainder. Yeah. So ex is t2. Sorry. Okay. So maybe I draw again. Ex is what? Ex is t2. Okay. Plus the remainder r2. Okay. So you should expect what? What should you expect here? What should you expect here? If I take t3, am I getting closer to ex or not? I should be getting closer to ex. Okay. Because you're adding more and more terms. Okay, you are getting closer to ex. Okay. So you will see that the remainder should be getting smaller, and smaller if you go to further end. Okay, so this is a theorem. Theorems read like this. So let's say, okay, if I split my f into the nth Taylor polynomial plus the remainder, okay, and the remainder, okay, go to 0. When n go to 0. Okay, if you take large enough number of degree of polynomial for these within the radius of convergence, okay, within the radius of convergence, then f is just equal to the sum of its Taylor series on the same interval. Okay, on the same interval. And so this should be what you are hoping for. Okay, so if you can write f in terms of some Taylor series, and then this remainder is really getting small and small, then they are actually equal. Okay, they are actually equal within the radius of convergence. Okay. So if the question asks you to show a function is equal to its Taylor series, what do you need to do? Okay, what do you need to do? You need to check the first equation here, and then check that the remainder go to 0. I think most important part is where you take this remainder go to 0. Okay. So let me see. So let's see how to show something is going to 0. Okay. So we need another property, okay, which is called the Taylor's inequality. Okay. So what's Taylor's inequality here? Let me introduce all these stuff to first, and then I will show you an example. So Taylor's inequality. So if the sum, if the absolute value of f to the power n plus 1 applied at x, okay, is less than or equal to m for some interval, okay, so some interval, okay, then what? Then the remainder Rn x of the Taylor series actually satisfy an inequality. Okay, actually satisfy an inequality. And so what's the inequality we have? Inequality, okay. So it tells us that not just the coefficient is bounded by m, okay, but the whole remainder is bounded by this m, is controlled by this m, okay. So the remainder is controlled by m plus n over n plus 1 factorial times, okay, the interval x minus a to the n plus 1. Okay, where does this live? Right? Where does this x live? Okay, so this s have to live where this inequalities here hold. Okay, so x minus a. Let's try and read again this inequalities here. Okay, so you know what is Rn here? So Rn here is a leftover thing. Okay, what's the leftover here? So remember what do we have just now? So we have f equals to Tn plus Rn. Okay, Tn is what? Tn is the term that add until n. Okay. So where's your leftover? Your leftover is coming from n plus 1 to forever. Okay. But in particular, the first leftover terms is what? The first leftover term is f to the n plus 1, okay, applied to a divided by n factorial x minus a to the n plus 1, and so on. Does it make sense? Does it make sense? Make sense? Okay. But what do we have? We have the first terms here. Okay. The first coefficient here controlled by an m. Okay. Controlled by an m within some interval here. Okay. Okay. Then what do we do? Then we can just bound. Okay, we can just bound everything else by m over n plus 1 factorial. Okay, seems like you can use, this is m plus 1. So it seems like you can just use the bound for the first term for everyone else. Does it make sense? Make sense or not? The thing after here is just Rn. Okay. So we're trying to use the first term to bound everything else. This is what this theorem gives you. Does it make sense? Any question you want to ask? If I don't ask you a question, you ask me, right? Okay. If you don't ask me, then I ask you. Correct. Yeah, try to ask question. Okay. Asking question is a very important process in your study. Okay? Yeah. Ask good question is the key to study. Okay. Any question? You know what we are doing now? We use the bound on the first term in our remainder, try to bound everything in the remainder. Okay, this is Taylor inequalities. And this is a very good project also. Your senior also did this as a project last time. Okay? No question? Don't you go question? Huh? Maybe? No? Then try us. Okay, maybe you can think a little bit more later. You can come back and ask me again. Okay, so so one fact you need to remember. Okay, so you need to remember that the following is always true. True. And what is true? So limit of s to the power n over n factorial equals 0. Okay. Equal to 0. Okay, for every real number x. Okay, so this is always true. Any idea on how to prove this? One way you can prove this is to use the epsilon n definition. Okay, you can use that to prove. The other way, maybe we need to do the example first and then we can use it. Okay, which is using the test of divergence. Okay, because what is this term here? This term actually appears as the summand inside the e to the power x. Okay, since the series converge, then the limit of an must go to 0. Okay? So this is the test of divergence applied on the e to the power x. Okay, but let us show that. Okay, let's show that. So let's show that. Prove that e to the power x is actually equal to the sum of its Maclaurin series. Okay. So we're trying to apply our theorem above. Okay. So we already write it. We already write it as some power series. Okay, right. We already write it as some power series. So we want to show that actually they are equal. Of Maclaurin series. So what's the formula? Sn over n factorial. Yeah. Okay, so what do we have to do? Okay. So by this theorem, we just need to show the limit going to 0. Okay, going to 0. So we wanted to show by theorem above. What we need to show is we need to show the remainder is going to 0 when n goes to infinity. It's going to 0. Okay. So what to do here? Okay. So we don't need to go too far. Okay. So we just need to take some d. Okay. Just check in some d is enough. Okay. And what we can see here is we can bound our n+1 term x. Okay. By what? Okay. How do we bound this? Okay. So this term here is bound by the condition on x. Okay, it's bound by the condition on x. Okay, so it really depends on this d here, but you can always find the d. Okay, so you just check it locally. Okay, and then this thing here is actually less than e to the absolute value of x, which is less than equals to e to the power of d. Okay. So what do you get? So by the Taylor series, Taylor inequalities, we already bound the first term of our remainder. Okay, this means that we can bound my remainder. Okay, so we can bound our remainder by what? So we can bound our absolute value of our remainder by exactly e to the power d over n+1 factorial. Okay, times x minus a in our case is 0, to the n+1. Okay, so we can bound this. Okay, but we still want to show that it goes to 0. Okay, so we bound it from the right. Okay, we bound it from the right by this number here. Okay. And this guy here, on the left hand side, okay, on the left hand side, what's the limit of this guy? Let's check. What's the limit of this guy here? E to the power d over n+1 factorial x to the n+1. What's the limit here? This is what we talked about just now. This is 0. Okay, why is it 0? This is just some constant multiply on x to the power n over n factor. Okay, so this goes to 0. Right? Okay. However, convergence of sequence. Still remember? If the sequence converge, you can just multiply a constant, it still converge. Okay. Okay, so this go to 0. Does this imply the left hand side going to 0? The left hand side also can go to negative, right? Maybe. But in this case, can you go to negative value? No, right? Because this is an absolute value. Okay, absolute value is always greater or equals to 0. Okay, so this means you can apply the squeeze theorem. Okay, squeeze theorem. Okay, so by squeeze theorem, left hand side and right hand side both converge to 0. That means what? Sequence E. Okay, and about SE. Sequence. Okay, this is squeeze theorem. The limit of Rn x goes to 0. Okay. So Ex is equal to the sum of its autonomic series. Okay, within the d, within this d here. We need a D here. Okay. We need a D here. We need D, right? But what can we do here? So this statement seems like it's true for all points. Okay, but our proof here only works for some D. Okay. Our proof here only works for some D. Can we really deduce anything for the whole line? Can we deduce anything on the whole line? Use anything for the whole line? Can we deduce anything for the whole line? Okay, let's take a break until 5:07 and then we will resume there again. Okay, what do you think about it? Hello, testing. Okay. So tired. A lot of assignment. From where? Every course got. Calculus. Calculus. Okay, good. Is it? Okay. I mean, in future you will experience the same. Maybe the other lecturer is like very lenient towards you, but I want to say that the difficulty of maths is never, I'll say, it's never easy. Yeah, it's never easy. If you feel easy now, you will feel painful later. Okay, I just want to say, if you feel hard now, then you'll get easy later. This is the nature law.
Now it's easy letter.
Yeah.
Now it's painful letter is not very painful again.
Huh?
Become the more painful.
No.
Not like this one.
Not like that. You will feel easier. Although maybe it's painful, but you'll feel easier. Okay. Yeah. So I prefer the latter. Yeah. Hope that.
Like that what you say.
Okay. Sure. Finger crossed. Okay, finger crossed. Okay. Let's see. So just now we mentioned about this, right? So we only check for x less than d. Okay. But this is true for all d. How to extend it to every point? How to extend the result to every point? How to extend the result to every point? Larry, I have an idea. Do you have any idea? Just say anything. Okay, so what's the question now? So, in the process of proving, right, to use Taylor inequalities, okay, so Taylor inequalities works within some distance, okay, from the center. Okay, so there's a D for the inequality to hold, okay, and then we use this constant here to bound our remainder. And this is how we show the remainder goes to 0. And then we say that the function is equal to its Maclaurin or Taylor series. Okay. But we know that EX is equal to the Taylor series or Maclaurin series everywhere. Converges everywhere. Okay. That one is true ratio test. Okay. But in this case, so how are we going to deduce the same fact? Okay, the same fact using a Taylor inequalities. Any idea? Any idea? To let D be arbitrary, we can, and then we can let B. I mean, D is actually arbitrary, right? We really start with arbitrary D here. See? We didn't have any condition on D. This D is actually arbitrary. Huh? What do you mean I pick n less than this one? We don't need to pick M anymore. This D is the... So the M produced by this D is e to the power D. So this is the M in the theorem. This was the M. Okay. Yeah, this D is an arbitrary D. And then does this tell anything or not? Does this shed any light? Mm-hmm. Mm-hmm. Uh-huh. And then we can see that the F is equals to the Maclaurin series within all these interval of convergence, and then yeah, correct. Okay, and then straight away deduce for whole real number. Do you straight away deduce it for the whole real number? What's the statement? What's the statement? So you see, if somehow you can write fx equal to some Taylor series, okay, and then you check that the remainder go to 0 within the some distance r, okay, then this f is actually equals to the Taylor series on that interval. Okay, so meaning just now we have the D, we on around that D only, but this D is arbitrary. Can we take limit of D or not? Can. So if it is true for all D, okay, if it is true for, let's say, so let me write something, the question I gave just now. So if it is true for all x minus a less than r, true for all r such that this is true, then is it true for is it true that is it true for taking r to infinity? So meaning just negative infinity to infinity. Okay. So if you are true for true for all interval, is it true for the whole real line? You get the question now? Yeah. Is this true? Okay. Think about it again. Okay, we will resume it on Thursday. Okay, we'll fix it on Thursday. Either you fix it or I fix it. Okay, let's fix it on Thursday. Okay. Not that. This condition here coming from this f equals to the sum of Taylor series. Okay, it's not random property. This it here is not a random property. This is the f equals to the sum of Maclaurin series. Okay, or Taylor series. Not random property. Maybe some property will be true, some property will be false. But let's say this one, is it true or false? If it's true for all finite interval, is it true for the infinite interval? Okay, so this is the question. Okay, everyone got the question ready? Yeah, got the question first, okay, before solving it. Yeah, no question about this. Understanding this question. Okay, try and see if you can solve it, or I will solve it on Thursday. Okay. So let's continue first. So let's do some standard question on Maclaurin series. So for example, find the Maclaurin series for sin x. Okay. And then prove that it really represents sin x for all x. Okay. So what do we do? Okay, so what do we do is we just compute what is f x, f prime x, and then f prime x, and then you keep doing it, and then until you get f to the nx. Okay, but you want Maclaurin series, right? So Maclaurin series centered at where? 0. Okay, you center at 0. So you need to evaluate all these values at 0 as well. Okay. So what do we have? So fx we have sin x. Okay, differentiating sin x you get cos x, and then differentiating cos x you get minus sin x, and then you get minus cos x, and then you repeat. Okay, you repeat the cycle. Okay, so and for f to the n derivative, you really rotate between these four function here. Okay, it's like a mod 4. 1, 2, 3, 4. Actually, mod 5. Mod 5, right? Yeah, the fifth one come back to the first one. Correct? Yeah. Okay. Do you understand what I'm talking about? Okay. So there's a cycle here. So if you differentiate minus cosine x, what you get? You get back to sine x. And then you repeat. Okay, and then you repeat. Okay. So in this case here, what is the value evaluated at 0? Evaluated at 0, you get f0, you get 0. F prime 0, you get 1. Again, f prime prime 0, you get 0. 0. And then f prime prime prime, f prime 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 0, you get -1. Okay, and then you repeat again. Yeah, so 0, 1, 0, -1, and then repeat. So sin x, using the formula, we should get 0 plus 1 over 1 factorial x plus 0 plus minus 1 over 3 factorial x cubed plus 0 and then so on. Okay. Still remember why we have an n factorial at the bottom? Remember the Cn, we need to divide by n factorial. Okay, so this n factorial pops up. So what can you observe here? What can you observe here? What's the power of this x? 1, 3, 5. What are these? Odd number. Okay, so these are the odd power of x. Okay, odd power of x. Okay. Sine function, sine x. Sine x is an even or odd function. Do you remember what's the sine function, even function and odd function? Can recall that. So what's the definition of odd and even function? Okay, if fx equals to f negative x is even, or is fx equals to minus x minus x. Okay, so in particular, sine function is a odd function. Okay, so you can see from the graph actually. Okay, sine is like this, right? Okay, but this is not enough to see these odd behavior. So you need to continue your sine function. Okay, so you can see that x and minus x. What's the change in this geometry here? Actually, you are reflecting over the y x equals 0 line, okay, or the y-axis, because you can see that my 1 is here, minus 1 is here, 0.5 on the right, minus 0.5 on the left. Okay, and then fx is equal to minus f minus x. Okay, so you pick 1 here, which is 1, and then you pick -1 here, you get -1. Actually, it's not -1, right? What's this point here? What's the point that give you 1 and -1? Pi over 2. Okay, so pi over 2 and minus pi over 2. Okay. 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 Yeah, so it's an odd function. In particular, you can see that all the power of x is odd. You see it? Okay. This is not a coincidence. This is not a coincidence. We are trying to dig more into this sine function. We are writing sine x in terms of polynomials. Okay, in terms of polynomials. But you need infinitely many of them, okay, to produce it. Okay. So you need infinitely many polynomials to produce your sine wave. Okay. And understand? Understand? Okay. So what should we do? So we need to check the limit of Rn go to 0. Okay, to show that they're really equal. Okay. To show that they're really equal, we need that. Okay. So this is some guessing. Okay, we have this guessing. So to show that it really is equal, we need to use the Taylor's inequalities. So to use Taylor's inequalities, we need to be able to bound the f to the n+1 derivative. Okay, we need to be able to bound the n+1 derivative. But what can you see? What are the derivative of f? What are the derivative of f? Sine, cos, minus sine, minus cos. So these values are really just less than bounded by 1. Okay, so the absolute value here is just always bounded by 1. So this gives the Taylor inequality. So if you can bound the first term of your remainder, you really can bound all your remainder. Okay, this is the power that given to you by Taylor inequalities. Okay, so bounded by what? Bounded by 1 over n+1 factorial times the some radius at d. Okay, radius d. Okay, and then you can see that go to 0 on the left hand side. Okay, left, right, on the right hand side. Okay, then by squeeze here, the limit of r and x actually is 0. Okay, and then similarly, using the same argument, I ask you to figure out it is equals to its Maclaurin series. And then you can actually check that the radius of conversion is also infinity. Okay, so it can fully represent it. It can be fully represented. At every point, it is equal. One way to do it, you can use the ratio test. And you can use ratio test to test it as well. Okay. Next. So next, how about finding the cousin of sine? So who is the cousin of sine? Cos. Okay. Let's find the Maclaurin series for cos x. So what is the thing you want to do? What's the thing you can do? What do you want to compute? Think. What did we do for sine x? What are the things we do with sine x? No. Yeah. Haven't. Also don't know. Sleep already. Yeah. Who else? Okay, Zhongyi. Hi, Zhongyi. What's the first thing we can do to find Maclaurin series for cos x? Okay, we find the n derivative, right? Okay, we find n derivative, and then we evaluate at 0. Right, Maclaurin series centered at 0. Okay, and then what do we do? And then what? Then we reorganize these terms. Okay, so it's this n derivative evaluated at 0 divided by n factorial times x to the power n. Okay, summing from 0 to infinity. And then you have to check that it really equals. What you need to check? You need to check that limit of your remainder go to 0. Okay, but to show this, you need to get the help from Taylor inequalities. You need to check Taylor's inequalities, okay, to get this limit here. But what does Taylor's inequalities need? You need to bound your remainder. Again, to bound your remainder, you need to bound the first term of your remainder. Okay, so how to bound your first term of your remainder? So you need to be able to bound your fn plus 1, okay, x, by some number, okay, some number. So how to get this number? So this number you need to investigate or to find from your function, the n plus 1 factorial, n plus 1 derivative of your function. Okay, so this really depends on your function. So you need to understand your function first. Okay, so this really depends on your function. But for our cos function, right? What's the derivative? Sine, similar to sine x. Okay, sine x minus cos x, sine x, so on. Okay, and then this has to be hold true for some interval. Okay, some interval. And then you can check that the limit go to 0, and then you use the theorem again. You deduce that cos x is equal to the sum of Maclaurin series. Yeah, so this is the standard way. You can do it. Repeat what we did for sin x again. Okay, repeat the same thing. But remember, we already learned one method, right? There's one method we already learned. Okay. Now we already, so let's show you the second method here. So what we have known, we know that cos x is the derivative of sin x. Okay. But just now we already find the Maclaurin series for sin x, and then we show that it's equal. So we can replace it. In particular, this is true for everywhere. Okay. When it's true for everywhere, then we can use theorem from power series. Okay, so really, power series and Taylor series actually is the same. Okay, what do you mean by same? I mean, yeah, they are the same. Yeah, they are the same. They are really the same because Taylor series give geometric interpretation to the coefficient of power series. Okay, power series just tells you that I can write this function as linear combination of power of x. That's all. Okay, but this Taylor tells you that that coefficient is special. You cannot simply put that coefficient into it. It is actually coming from the n derivative of your function. Okay. So there's a geometric meaning to the Cn, which is the n derivative divided by n factorial. Okay. So we can apply the power series theorem that we can differentiate term by terms. Okay, we can differentiate term by terms. We can differentiate term by terms. And then what do we get? And then if we quickly compute it, we just get minus 1 to the power n, 2n to the factorial, and then x to the 2n. Similarly, we keep the radius of convergence. Okay, so there's a significant here. What's the power of x looks like? What's the form of the power? 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 Even. Okay, 2n. 2 times any number is an even number. So you write cos x as a sum of even power. Cos x is an even function or odd function? Even. So this match up with the even function property. Okay. Okay. So just now sine match up with odd function expressed in terms of odd power, even function expressed in terms of even power. Okay. Okay, so this is for the Maclaurin series of cos x. And then maybe I just leave you to do other things. For example, you can do it for x times cos x. Okay. So how do you do x cos x? You know cos x already, right? So how to do on x cos x? See, you know cos x already. What do you do for x cos x to find Maclaurin series? Huh? No, I want you. I don't so fast give up there. X times cos x. Okay? So think about it. X times cos x. Okay? You already know about cos x. So what do you do for x times cos x? 还是你要我讲华语？啊？讲什么语都没有用。再听一次，很简单的东西吧，你什么都不用懂啊。咯 yeah, just multiply. Yeah, just multiply to the previous answer. Okay, yeah, that's all. Yeah, okay, 没有很难的，我不会每次骗你的 ，OK 。Okay. Yeah, so I'll try to do this, and then there's one very involving homework. Okay, this one is very involved. Maybe you can try at home, but if you really cannot do it, maybe you can do it together. But I already put out the question. I'll put out the solution. So it's the binomial series. This question is quite involved. Okay, so binomial series, which is what? Which is this? So it is 1 plus x to the power k. Okay, try to find the Maclaurin series for this guy, and then show that. Okay, show that it is convergent. Okay, it is convergent for x less than 1. Okay, it's convergent for x less than 1. In fact, this question can be generalized to k in a complex number. You can generalize to k in R and then complex, and then generalize to k in complex number. Yeah, if you are interested, you can write a whole thing about this binomial series. Okay. Yeah, we won't do this in class because it takes up a lot of time. And then the other easy one, and you should do, is this one. Okay, this one is an easy one. Then you should do it. It's 1 over 1 minus x to the power square. Okay, this one is easy. Okay, so this one easy, this one hard, this one easy. Okay, yeah. I'll put out solution, so no worries. So yeah, so let's see what we have done. So let's see what we have achieved already. So these are the Maclaurin series that we have achieved. So the first one is the one that I introduced, is the sum of just power max. Right? This one we use geometric series to show it. Remember? And the second one is through integration of the first one. Integrating the first one. And then the third one we haven't really shown it, but I asked you for homework. And then the fourth one we use the ODE. And then the second method we use Taylor series. Okay, we have used 2 methods to find this equalities here. And then sine x, cos x is what we did just now. And then this one is the one I asked you to find. Okay. Yeah. You know why that's called binomial? No? Did you learn in discrete the Pascal triangle sum? Pascal triangle. When you expand it, you get a Pascal triangle as your coefficient. Yeah. It's this thing. Okay, this is a generalization. And this k is anything. The k you consider is natural number, right? 1, 2, 3. And this one can be complex as well. Then you need to see how they define the power. Okay. Okay. In that case, I think maybe we will skip all those things. There are some example in the some more example in the lecture notes. You can try it out. Maybe we just skip those and come back if we like. And there's a part on the application of Taylor polynomials. Okay. I won't do it in class. You can try and learn it. Maybe I won't put emphasis on this chapter, this section. Okay. Yeah. If I need to test it, then maybe we'll come back again. Otherwise, you just learn it from the note. Is it okay? Yeah. So I try to leave all the application stuff for you guys to do. Okay. And then I'll focus on the pure side. And then we will test more on the pure side. Okay. 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 Yeah. Okay. Yeah, because the pure side is more towards my expertise. Yeah, I'm more towards pure maths. Okay. So if you want to get most out of me, is to do more pure maths. Yeah. Otherwise, I cannot offer you much. Okay, yeah, that's why I choose to go that way. But let's see. I'll see your standard first. So I will see your assignment 1, how you go, and then we will see how to adjust. Okay. Yeah, so please doing good. So assignment is the chance for you to increase your result. Because why? You have most time doing your assignments. Okay, you have 2 weeks to do your assignment. You have all the resources. You can go online, check with friends, check book, check everything, check until correct. 100% give to me also can. The only thing I request from you is don't just copy blindly. That's all. Understand the solution. Write it in your homework. That's all. Okay. Reference, give reference, and then say who you work with. That's all. Okay. That's all. Okay. So assignment, you cannot give up on your assignment. Do it well. Okay. Do it well. Yeah. Understand your assignment. Okay, and assignment is the place I can give you feedback. Given these 7 minutes, let's go into a little bit about this Fourier series, and then we will come back on Thursday. Okay. So next part is about Fourier series. Okay, just now the thing we sum up is power of x. Okay, just linear stuff or quadratic curve, and then S cube curve, and so on. Okay, but now Fourier's. So what does this Fourier does? Fourier is a person. I think it's a French. Okay, Frenchman. So he studied heat equation. Okay, he studied how things heat up. Okay, heat can be conducted in a waveform. Okay, so he in particular he is interested in wave. Okay, wave. So for example, what kind of wave you already see in the class? Yeah, sine wave, cos wave, okay. Sine wave, cos wave. So these are actually the building block of our series here. So we're adding up cos and sine together. Okay. If you go deep enough in your linear algebra, I'm sure have you guys gone into it. So sine x and cos x are linearly independent. You can go and find your textbook. Okay, you can show it. So they form a basis. Okay, and then you can take power of them and then add them up. Okay, so you form a series. Okay, and then you put coefficient in front of them. Okay. So what I'm describing is here. So for example, if you have a first curve like this, okay, and then you somehow want to add these two curves, how do you add two functions together? Yeah, you add at each point. Okay, so they sum up at each point here. So each point here, they add up together. Okay, so this is what we say about f. So f plus g at a point is what? Is really just fx plus gx. Okay, so this is the definition. So when this definition, right, I'll put this semicolon dot dot equal. Okay, dot dot equal. So this is definition. And then you can see that if I add them up, I will get this new curve here. And you can see that the first point here actually go above 1. Why? Because there's a positive contribution from the other one. And then for some of them, they cancel out. Okay, you can see that. For some of them, they add up. So the amplitude increase and then some of them decrease. Okay. Understand? Okay. So, for example, how to use sine wave to make a square wave? Okay, how do you use sine wave to make a square wave? You can see that this square wave, right, a bit unnatural. This is actually not a function. Not a function. Right. Seeing is square wave a function? Why not? What? Why what she said? Too ugly. How do you define ugly? Not beauty. How do you define beauty? So this is going through a circular statement, right? Okay. So why is it not a function? Function need to satisfy what? No, not one to one. It cannot be one to many. Okay, it will be well defined. One thing cannot send to two things. But here, what happens? You see a straight line there, a straight line there. So actually, it's not a function. Okay? So what is the best thing we can do is we can make this straight line as close to straight line as possible. Okay, that's the most we can do. Okay, we cannot make it really vertical. Okay, so in the textbook will say a function need to pass a vertical test. So meaning you draw a vertical line, you can only meet one point. Okay, but if you draw a vertical line here, then you meet infinitely many. Okay. So the best you can do is a bit slanted like that. Okay, arbitrarily close to this vertical line. Okay, so how are we going to do this? So let's start with sine wave. Okay, so first let's start with sine wave, the normal sine wave. Okay, and then we can add another sine wave. Okay, maybe like this. So what we do, we change the amplitude, we change the period. Okay, we change the period, we change the amplitude, and then when we add up, somehow we get this. We get two crusts. We get two crusts, and then two hump on the other side. Okay, and then what can we do? You can see that this part here getting a bit slanted more already. Okay, but here we have like this wave. Okay, but let's see. Let's us add more. Okay, maybe we add more terms. Then we'll get more wave on the crust and the crust. Okay, and then we're getting slanted more towards the vertical line, and then we keep doing it, and then we'll see this. Something like this. Okay, And then you can see that if we do infinitely many times, it really converges to the square wave. Okay, square wave. Okay, you should imagine more and more and more and more. Actually, see this in your this similar behavior in your life, in the application in your life. What is it? It is flickering, but somehow it looks constant. Huh? Why is it broken? Not only broken, it's a normal light also like that. Normal light is like that. Your light bulb is using AC current. So meaning it turns on and off, on and off, on and off, on and off. But the speed of on and off until your eyes cannot recognize it. This is the refresh rate, right? Refresh rate in your phone. Refresh rate in your phone. Refresh rate in your phone is also similar. Okay. 60 hertz, 120 hertz. Okay. Yeah. Okay, I think we stop here and then we'll continue on Thursday. If you really need help, you can contact me tomorrow office hour or message me, email me. By the way, I really want your original answer to question. What's the question I put on the halving the question 4, 5, huh? Okay, I want your own original idea on that question. Okay. Yeah. Okay. You write in your own word your idea. Wrong, never mind. Very stupid, also never mind. Very crazy, I like. Okay.
Very crazy.
As crazy as possible. Okay, but don't lie. But don't lie. Okay. I don't. Yeah.
上课如果补课不是有补房间吗？你们是在哪里补课？